Yeah, okay. So today we are going to discuss isometries of hyperbolic spaces, and then we will start discrete groups of isometries. Let me remind that last time we proved the theorem that there are only, so it's from the previous lecture, there are only three types of isometries in the hyperbolic space HD. So the first one, elliptic. The second is parabolic type, and the third one is hyperbolic. Recall that we distinguish these types by the number of fixed points. And well, in fact, the first, it's not like the number of fixed points. More precisely, in the first type, we have fixed points in HD. So here it is not empty, right? While in these two types, the fixed point set in HD itself is empty, but we may have here, so we will have here in the parabolic case precisely one. So the fixed point set on the boundary of HD is just 1 point. And in the third case, the fixed point set of the extended F on the boundary is precisely 2 points. Okay, so in fact, like the picture, let me just draw a picture. We have three types. So for example, it can be reflection, and then we fix the geodesic. The parabolic case, it is the rotation around the point. Well, it's one of the examples. And among the hyperbolic examples, we have translations along geodesics. And then we have one attractive fixed point and one repelling fixed point, okay? So I would like to discuss first how do these isometries look like in other models. And okay, and for example, let me take the I think the upper half plane model, upper half space model. So in the upper half space model, UD, we consider points. So let me write it this way. X is going to be X1 and so on, XD, right? Where XD is positive number. Then elliptic, okay, elliptic guys are just some elements that have fixed points in the upper half space. I would say that you can, one can think of this in the two-dimensional case and try to write down this Möbius transforms. I'm a bit more interested now in parabolic and hyperbolic isometries. So then parabolic isometries, fixing, so let's assume that let F be a parabolic isometry. Such that it fixes the infinity. Then Parabolic isometries are known to preserve the Horo spheres. So let me take, so this is the infinity, this is 0. So then f, then f leaves invariant the Horo spheres centered at infinity, which are the Euclidean hyperplanes. Orthogonal to the axis xd. Okay, so this geometrically looks like that. In the matrix form, one can write f of x as follows. This is going to be, so let me assume that this is a column of coordinates, right? X1 is on xd. Then we do the following. We preserve xd, right? But here we write something like that. We take the matrix A applied to the d minus 1, to the first d minus 1 coordinates of x, and takes plus some vector b1 and so on, bd minus 1, right? And then the last coordinate is still xd, okay? So what is this transformation? This transformation is in fact, so you see the coordinate xd is preserved, right? So our hyperplanes are defined by the, so this is the x is xd, right? So the hyperplane is defined by the equation that the coordinate xd is equal to some constant c, right? Okay, then this transformation is just some Euclidean isometry in this d minus 1 dimensional Euclidean space, okay? And here, this A, so I should write where A belongs to the orthogonal group of order d minus 1, right? Here I use the word Horo spheres, and I didn't say what is like how the Horo spheres are defined, and I can actually give this definition. So a horosphere centered at the infinite point is basically just a hypersurface orthogonal to all the geodesics passing through the point P. So by definition, a horosphere centered at the boundary point P is a hypersurface orthogonal to all geodesics starting at the point P or ending, right? Starting at P. So let us consider the spheres in different models, but I will need colors. Okay, so let me take this one and this one. So in the Poincaré model, this looks like that. I have, actually it's similar to start with the upper half plane model. So in the upper half plane model, let P be the infinite point, right? Then my geodesics starting at the infinite point are precisely all vertical half lines. And thus our spheres are Euclidean hyperplanes, right? So these geodesics are our geodesics starting at infinity are all vertical half lines. And thus we see that our spheres are Euclidean d-1 dimensional hyperplanes. Okay, thus the horospheres are the Euclidean hyperplanes. I would say the horizontal Euclidean hyperplanes. Defined by xd is equal to some constant. So this is in the upper half plane model. Sorry, in the upper half space model. In the ball model. So now let's consider BD, and P is just any point from the boundary sphere. In this picture, one can consider point P right here, and we have all the geodetics and so on, right? And one can notice that geometrically this, so if you take a sphere passing through, so if one takes a sphere, the red one sphere, passing through P, such that the sphere that is tangent to our boundary of the hyperbolic space, then this is going to be orthogonal to all geodesics passing through P, right? So if you do this picture, you will see that all these are orthogonal. And definitely we have many horospheres at the same point, right? So we have here so one can vary the number xd, right? Basically this constant here, and then we have different horospheres on different levels. And same here, we can also take this sphere, and so on. Okay, it is interesting how do these horospheres look like in the hyperboloid model. So in the hyperboloid model, one can describe the horospheres as follows. In the hyperboloid model, P is some isotropic vector by some point such that the scalar product, the Lorentzian scalar product of P with itself is 0. Then the horosphere okay, I would say that I describe some arbitrary so a horosphere at P is the set of points. So okay, I will take the points from HD such that the scalar product of X with P is also some constant. Okay, and geometrically it looks like this. We have this hyperboloid model. We have our hyperboloid over here. And then I decided to choose one isotropic vector as my boundary point. Then what does it mean that the scalar product is constant? It actually means that I'm taking some cone, right? So basically, okay, so geometrically I should take okay, maybe it's not, yeah. So let me think again. It's yeah, so I'm taking the cone. Yeah, okay, so this should be, I think this should look like that. Great, this is my cone. And after you project it down to, okay, so let it be, let it be the south pole of my hyperboloid. And then after I'm taking, so basically I need to include all this ones over here, right? And this gives me, this is the projection to the, so this is my HD, and this is my full model BD, right? Then after the projection, I obtain the sphere that is tangent to BD, okay? Well, why are these horospheres interesting? One can show that geometrically horospheres are indeed Euclidean d-1 dimensional spaces. And one can do it by restricting. So, for example, by restricting the scalar product onto the sphere, one can obtain that this is the Euclidean manifold. Okay. So for example, by restricting the hyperbolic metric GH onto sphere. Okay, so once you know how the horospheres look like, then one can indeed show that the horospheres are. So in fact, the strategy is basically this: you first describe the horospheres, and then you notice that parabolic isometry fixing the infinity leaves invariant horospheres. First, you show that horosphere should be mapped to, so that horospheres are sent to the horospheres, and then you can prove that in fact the horosphere of the level C1 cannot be sent to another horosphere at the level, say, C2. And then it gives you this description. So our parabolic isometries are precisely the Euclidean isometries along the hyperplanes, which are our horospheres at infinity. Okay, that's how it can be obtained. Okay, so it is about Euclid. Okay, it is about parabolic isometries. Now about hyperbolic isometries. Let us move to the right. So the hyperbolic isometries. The hyperbolic isometries into models in UD. Okay, actually, probably I can do it in 3 models in. Okay, let's make it so far for UD and the hyperboloid model. In the upper half space model, so in UD, f of x is just lambda. So again, it is the vector, the column of coordinates. Here, I will write xd, while here I'm writing a multiplied to the first d minus 1 coordinates. So where lambda is greater than 0, lambda is not equal to 1, and A is the orthogonal group, is an orthogonal matrix of order d minus 1. Okay. And notice that if lambda is equal to 1, then you get, and you would probably get a parabolic isometry, right? And lambda is, so like a typical example is just, well, a special case, right? A special case. In dimension 2. It is just z to lambda z, where lambda is greater than 0, lambda is not equal to 1. So this is my fixed point 0 and infinity, and thus it just scales, right? So z, lambda z, assume that lambda is greater than 1, then my attractive fixed point of this hyperbolic transformation is the infinity, okay? And 0 is the repelling. If lambda is less than 1, then any orbit here will just converge to the 0 point, right? This is my upper half space description for the hyperbolic isometries. Okay, now let us think about this isometries in the hyperboloid model. Then recall the following. So this is in UD, now in HD. I can say that this is my hyperboloid, right? And my geodesic is just, it is actually uniquely determined, right, by two endpoints. So as here, okay, I will do it. So like geodesic in the ball model, right, I have a geodesic with two fixed points, P and Q. These P and Q in the hyperboloid model are just some isotropic vectors, right? So P and Q. Then I can change the basis. Let's change the basis for RD1. So I am considering the basis P, Q, and something else. This is motivated by the following decomposition. I am basically taking P, the span, like the linear span of P and Q, plus its orthogonal complement, okay? So span of P and Q and its orthogonal complement. In this basis, my hyperbolic transformation in this basis, okay, in this new basis, right, in this new basis, hyperbolic isometries look like, so the hyperbolic isometry preserving P and Q, okay, a hyperbolic isometry, there are still many, so the hyperbolic isometry fixing E and Q has the following form. It is the diagonal matrix, so it should be, in fact, I will have some lambda, 1 over lambda. So here we have zeros, and the remaining coordinates are 1. So I can reformulate it as follows. Hyperbolic isometries are those that are conjugate to diagonal matrices lambda, 1 over lambda, and the units on the diagonal. And here, actually, so here, lambda is equal to the exponent of mu, and mu is the displacement. Displacement means that my hyperbolic transformation takes the point x. So let us think about points from the geodesic. So it goes, okay, actually, if this is greater than 1, let's suppose that mu is greater than 0, then in fact this converges to infinity and this converges to, right, let me think. Okay, yeah, so in this case the x is sent to the point y, okay, f of x, and the hyperbolic distance between these 2 points is precisely mu. So the hyperbolic distance between x and f of x is precisely mu, right? So this is the picture. So the only point is, so if lambda is, it depends. If lambda is greater than 1 or less than 1, depending on that, you decide if P and Q are attractive for repelling fixed points. Okay, so it just depends on the, basically depends on the sign of mu. Mu should be positive, so since it's just the, but if it has the sign, then it basically tells you you move along from P to Q or back. Okay. Okay, I think that's yeah, this is what I was going to tell you about the types of hyperbolic isometries in different models. And now I guess we can make a short break and then I will continue. I think then I will continue the discussion of discrete groups of isometries. Okay, before we start the discussion of discrete groups of isometries, I also want to give you the following, actually, I can call it proposition. So, proposition. Okay, let F, let F be an isometry of the hyperbolic space, then the following holds. If F is elliptic, then, okay, so D is greater than 1. And also I would like to add that and let K be some integer greater or equal than 2. So it belongs to integers. Then, in fact, any power of an elliptic isometry, then Fk is either elliptic or trivial. And if it is parabolic then Fk is parabolic and respectively. So here is basically I'm repeating the same. And if F is hyperbolic, then F to the power of K is also hyperbolic. Moreover, finite order elements can only be elliptic. So if F to some power S is the identity, then F is elliptic.